Good day. Today we will continue our conversation about the chemistry crystallography, the basis terms. And we will tell about the coordination number and coordination polyhedron. Here you can see the plan of our lecture. In the beginning, we will repeat the following regularities of the ionic radius because it is important, and then we will talk about the coordination number and coordination polyhedron and the examples of this definition. The dimensions of the ionic radius obey the following regularities. I remember see this. The first within one vertical series of the radius of ions with an identical charge increase with increasing atomic number. You can see here little radio, big radio. For the same element increases with the radius of the negative charge and decreases with increasing positive charge. A radius of the anion is greater than the radius of the action anion because there is an excess of electrons and the cation's deficiency. The red balls the cation and the blue balls are the cations, anions, and you can see that of course the anions are bigger than cations. And the third, the size of atom and ions follow the periodicity of the table by Mendeleev, exception number 57 to 71 and 89 to 103. The third statement you can see on this illustration, increasing the ionic radius, and here on the vertical series of radius. And in conclusion, we can say that the effective radius of the ion depends on the atomic number and degree of ionization. Coordination number of the atom or ion is the number of the nearest neighbors of the same type of atoms or ions. It is very important of the same time, not any type of atoms in the crystal structure. If the centers of these atoms mentally connect with each other by the straight lines, in the general case is obtained by coordination polyhedron. Atom for which the polyhedron is constructed is located in the center. Coordinated polyhedron doesn't require the external structure or shape of the crystal and does not meet it. Here you can see the simplest coordination polyhedron. For example, dumbbell. Coordination number equal to B triangle. Coordination number is 3. Here you can see 1, 2, 3. Below tetrahedron, coordination number is 4. 1, 2, 3, 4. And this polyhedron is a bit of complicated. It is a cube. Coordination number is 6. Here you can see the cuprum structure, and on the illustration of its cuprum structure we will determine the coordination number and coordination polyhedron. A copper atom is a small amount has two oxygen atoms as best neighbors at a distance. Thus, coordination number kappa for oxygen is 2. Another coordination number is number of oxygen number for kappa is 4. Oxygen's atoms 5 have 4 main numbers of atoms 10, 11, 12, and 13. Consequently, the coordination polyhedra are respectively a double band and a tetrahedron. Another example, the ferrum structure. Let's begin to describe the crystal structure of iron. At the vertex 4 of the elementary cell, 3 mutually perpendicular edge 1, 2, 4, 3, 4, and 9, 4, taken as the coordinate directions. The elementary cell is a cube since all its edges are equal in size. In accordance with the definition of translations, the above-mentioned edges are basic translations. Let us assume and consequently all coordinate angles are right. And in conclusion of this short video, I want to tell about the new hypothesis. This hypothesis was created in the early 20th century, because in the early 20th century a fairly large group of substances was discovered. The value of the atomic distance is determined only by the presence of one type of atoms and totally dependent on the presence of the same structure of atoms of other varieties. Of course, it was the contradictions, and these contradictions was explained by the theory of dense spherical packing, or the theory of close packing, and this theory we will discuss on the next lecture. Thank you.